My name is Amy Huff, and I'm a research scientist at Pennsylvania State University. I'm also an air quality forecaster for the Philadelphia metropolitan area and the state of Delaware. Today, I'm going to discuss how aerosol products can be used to help predict the impacts of wildfire smoke on ambient air quality. I'm going to focus on air quality forecasting, but aerosol satellite products are equally useful for forecasting visibility associated with smoke. To start, I'd like to give a very brief overview of operational air quality forecasting. Air quality forecasting is a bit different from weather forecasting, which is done by a federal government agency, the National Weather Service. In contrast, air quality forecasts are provided by state, local, and tribal government agencies. Currently, forecasts are issued for regions in over 40 states and the District of Columbia. The most commonly forecasted pollutants are ozone, fine particulate matter, or PM2.5, and coarse particulate matter, or PM10. California also issues forecasts for nitrogen dioxide and carbon monoxide. Forecasted and observed pollutant concentrations are communicated to the public using EPA's Color-Coded Air Quality Index, or AQI. The AQI scale ranges from green, or good, yellow, which is moderate, orange, which is unhealthy for sensitive groups, abbreviated USG, red, which is unhealthy, and purple, which is very unhealthy, and maroon, which is hazardous. Forecasts are valid for the next day, in other words, tomorrow, and most agencies have a mid-afternoon forecast deadline, although some agencies issue morning forecasts. The main implication of the early afternoon forecast deadline is that forecasters need all data and guidance that are used as input to the forecast by about 1 to 2 p.m. local time. If you are interested in your local and state air quality forecast, it is available from EPA's airnow.gov website. Ambient air quality is influenced by transport of air from upwind locations, among other factors. The chemical composition of PM2.5 varies by location and time of year, but during the fire season, a critical component can be smoke from wildfires. Wildfire smoke can travel long distances, sometimes hundreds of kilometers downwind. If the smoke is thick enough and it mixes to the surface, it can cause exceedances of the National Ambient Air Quality Standard, or NAAQS, for PM2.5. The current daily PM2.5 NAAQS is 35 micrograms per cubic meter, averaged over 24 hours, so that's midnight to midnight local time. Observed code orange or higher PM2.5 on the AQI scale corresponds to an exceedance of the National Ambient Air Quality Standard. When forecasters expect the NAAQS will be exceeded, they issue an Air Quality Action Day Alert, or AQA alert, which warns citizens to take actions to protect their health by limiting strenuous outdoor activities. It's important to note that for most locations in the CONUS, smoke is an unusual event. For example, transported smoke typically only impacts the Mid-Atlantic region a few times per year. But fire seasons keep getting longer and more intense, so transported smoke is becoming more of an issue for downwind forecasts. Smoke is an issue for air quality forecasting because none of the traditional tools we use as guidance are skillful for transported smoke. For example, 3 of the most common forecasting tools are climatology, persistence, and numerical model guidance. As I mentioned, smoke events are rare for most locations in the U.S., so they are not reflected in climatology, which uses historical observed PM2.5 concentrations as guidance for forecasts. Persistence, which uses today's observed PM2.5 as a forecast for tomorrow, cannot account for the first day of a smoke event, but it can be helpful for subsequent days if a smoke event occurs over a multi-day period. Current numerical PM2.5 air quality models do not include transported smoke in their boundary conditions, so they cannot capture any increases in ambient PM2.5 at downwind locations due to contributions from smoke. So when air quality forecasters suspect that transported smoke plumes may impact local air quality, they turn to aerosol products from satellites to follow the track of the plume and predict whether it will mix to the surface. The recent Fort McMurray fire in northeastern Alberta, Canada, is a case study in how satellite aerosol products can provide information on smoke transport and its potential for impacting surface air quality. The Fort McMurray fire burned for more than a month, consuming over 600,000 hectares and forcing the evacuation of almost 88,000 residents from the city of Fort McMurray in early May 2016. Satellites provided spectacular imagery of the Fort McMurray fire, including the aerial extent of smoke plumes and a quantitative estimate of smoke aerosols as aerosol optical thickness, or AOT. This is a true color image, abbreviated RGB, of smoke plumes from the fire on May 7, overlaid with fire radiative power, abbreviated FRP, hotspots. Those are the red spots. All data are from the VIIRS instrument on the SWOMI NPP satellite. You can see the thick gray smoke plumes emanating from the fire locations and streaming southward. For more information on the VIIRS aerosol products, view the separate tutorial that reviews the products in detail. The thick smoke plumes from the fire reached the northern plains of the U.S. and mixed to the surface on May 7th, causing high ambient PM2.5 concentrations in 4 states: Minnesota, Iowa, Nebraska, and North Dakota. You can see the locations of the highest daily average PM2.5 concentrations on this AQI map here for May 7th. PM2.5 reached the unhealthy code red range in Iowa and Minnesota, with code orange or unhealthy for sensitive groups levels in Nebraska and North Dakota. Remember, levels at code orange and higher are exceedances of the daily PM2.5 National Ambient Air Quality Standard. This was a one-day event, with PM2.5 dropping down to the safe code yellow range across the region on May 8th. This is a graphic of the daily forecast guidance from the 12 UTC run of the National Air Quality Forecasting Capability numerical model on May 7th, showing the predicted daily peak PM2.5 concentrations for May 7th. The scale on the left is in concentration units of micrograms per cubic meter, and it is color-coded to the AQI scale. You can see that because the model does not currently include smoke in its boundary conditions, it didn't pick up on the transported smoke from the Fort McMurray fire. And in fact, the model predicted widespread, very clean, code green PM2.5 concentrations, in contrast to the observed concentrations in the code orange and red ranges. This is the aerosol optical thickness, or AOT data, from the VIIRS instrument on the SWOMI NPP satellite for the northern plains on May 7th. VIIRS clearly shows the smoke plumes from the Fort McMurray fire streaming southward, so these are the red, yellow, and orange colors, streaming southward into the northern U.S. plains. The VIIRS true color imagery is overlaid on the AOT imagery, and you can see several areas of thick clouds in bright white that block the measurement of AOT. Even with the presence of some clouds, however, the transport and aerial extent of the smoke plumes are evident, as well as the high concentrations of aerosols, or PM2.5, in the smoke. Since AOT is a column of measurement, it does not provide any information about the location of an aerosol-rich plume in a vertical column of the atmosphere, or its likelihood to mix to the surface. Forecasters need to predict whether a smoke plume will impact surface air quality. If the plume stays aloft, we don't really need to worry about it. To meet this need, NOAA provides 48-hour forward aerosol trajectories based on observed aerosol optical thickness, AOT. These trajectories are initiated from areas of high observed AOT, so that's AOT values greater than 0.4, and the trajectories run 48 hours into the future in 3-hour time steps using meteorological predictions from the 12 UTC run of the NAM meteorological model. The pressure levels of the trajectories are plotted in millibars and colored to a magenta-white scale. As the forecast trajectories progress in time, magenta-colored trajectories indicate a flow of air towards the surface, with a potential similar movement of aerosols. White-colored trajectories indicate upward movement of air away from the surface. So the idea is that where you see magenta trajectories, smoke plumes are expected to impact the boundary layer. 850 millibar wind field vectors are also plotted as white arrows to show wind direction and speed. Locations where forecasted 3-hour accumulated precipitation is greater than 2 kilograms per meter squared are shaded yellow and represent the potential for wet deposition in areas of high aerosol loading. The 48-hour aerosol trajectories run on May 6, shown here, predicted that the Fort McMurray smoke plume would mix to the surface over the northern plains on May 7. The magenta and pink lines show the south and southwestward direction of the transport of the aerosol-rich plume, which is located over southern Saskatchewan and Manitoba on May 6, and those are the red, orange, and yellow colored AOT regions that you can see near the top of the image. So the magenta and pink colors of the trajectory lines, so those are the streamers that are coming off of that high AOT area, and they're moving kind of south-southwestward. So these magenta and pink colors of the trajectory lines indicate that the smoke plume would remain close to the surface as it moved into eastern Montana, North Dakota, South Dakota, Minnesota, and Iowa on May 7th. And that's exactly what we saw happen. Near real-time and archived aerosol products from VIIRS are available as part of a new blended fire and smoke product called the Enhanced Infusing Satellite Data into Environmental Applications, or eIDEA website, shown here. You can find eIDEA by Googling NOAA eIDEA or by typing in the eIDEA URL shown at the top of the page here. eIDEA also has archived imagery going back to February 2016. eIDEA's domain covers the continental United States, Alaska, and Canada. The domain will be expanded to include Mexico, Central America, and the Atlantic Ocean in the near future. eIDEA was designed to specifically address the needs of forecasters who require timely data and imagery on wildfire smoke in a simple, easy-to-use interface. eIDEA includes the forward trajectories to predict when smoke plumes will reach the surface at downwind locations, as well as current PM2.5 ambient concentrations, which indicate where smoke is presently impacting surface air quality. This new tool from NOAA is being used by air quality forecasters and NOAA incident meteorologists, or IMETs, to track the effects of wildfire emissions during the 2016 fire season. For more information on how to use and navigate eIDEA, view the separate tutorial on eIDEA. The eIDEA website will be updated after the launch of the GOES-R satellite in November 2016. GOES-R is the first in the next generation of geostationary Earth observing satellites. It will have a sensor similar to VIIRS called the Advanced Baseline Imager, or ABI, that will be capable of providing aerosol observations every 15 minutes over the full disk of the Earth, covering North and South America. In this way, the GOES-R ABI will provide nearly continuous, high-accuracy aerosol observations of the atmosphere over the Western Hemisphere. The GOES-R ABI will also be able to scan the CONUS every 5 minutes in certain situations. Critical events, such as wildfires, will be monitored on a special mesoscale mode that will provide a rapid update of observations every 30 seconds. Since VIIRS data are from the SWOMI NPP polar orbiting satellite, with an early afternoon overpass time around 1:30 p.m. daily, often VIIRS data are not available in time for early afternoon forecasting deadlines. But nearly continuous geostationary observations from the GOES-R ABI will give forecasters timely information about fires and smoke. With aerosol and cloud imagery available at 30-second intervals from sunrise to sunset, data from GOES-R will become indispensable for forecasters who need to assess the impacts of smoke to help protect public safety and air quality. It's difficult to overstate the importance of aerosol satellite products, such as those from VIIRS, for operational forecasting during smoke transport events. We've seen that the tools forecasters rely on, including numerical model guidance, are not generally useful for smoke transport cases. This leaves the aerosol satellite products, particularly the aerosol trajectories, to show the transport and extent of smoke plumes. The aerosol satellite products give forecasters a heads up when smoke may be heading their way. The satellite data can also be used in conjunction with surface PM2.5 observations across the CONUS and Canada to determine when smoke is mixing to the surface. And the 48-hour forward aerosol trajectories are critical for determining if aerosol-rich smoke plumes will mix to the surface. The new eIDEA website is a great resource for forecasters to access the new generation of satellite aerosol products, including the trajectories.